Hello, all, and welcome to this Surface Ventures Mini-Symposium on the AFM characterization of energy materials. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and material science education for both academia and industry. It'd be great for you all to type in the chat and tell us where you're joining from. It's always good for us to see where you're from and, basically see, and learn more about our audience. Today, we'll be having multiple speakers. Our first will be Professor Dr. Florian Hausen and Dr. Inhi Park from Jülich in Germany. Which we'll get to in a moment. Just a little more introduction from me. As we go along in the event, and as we have multiple speakers, please type your questions specific to each speaker in the chat. I will be marking them for the Q&A, which will follow after each speaker. Okay, we're planning to go for around 120 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. It'd be great if you would post these and tag us on LinkedIn after the event. For all of you that have registered, you will get a copy of the replay, so you will be able to review anything from the event that you may have missed. So, without further ado, let's welcome our first speaker to the stage. So, Florian Hausen is a professor of applied interface electrochemistry at RWTH Aachen and is acting department head for the microscopy and diffraction division at Jülich. Dr. Inhi Park is a postdoc at the same institution after graduating from the University of Bonn in 2022, and both speakers have a long-standing experience in electrochemical scanning probe microscopies and are interested in operando studies at interfaces in energy materials, correlative microscopy and spectroscopy, as well as mechanical properties and tribology under electrochemical conditions. Welcome both. Great to have you with us.
Yeah, thank you, Sam, very much for the introduction. I will start sharing my slides. I would also like to welcome all of you. So I will start with the presentation and I will hand over to my colleague, Dr. Inhi Park, and then I will show you something after that as well. So thank you very much for your time. Also, thank you very much, Surface Ventures, and also Bruker for giving me the opportunity, and Inhi as well for showing some of our research. And we're looking especially at chemical atomic force microscopy. And as I've learned from former webinars, that there's a huge interest in friction and tribology among you. So we will focus on electrochemical friction force studies to understand energy materials. So first of all, I would like to give you a brief introduction into the Institute of Energy Technologies here at the Forschungszentrum Jülich in Germany, where we are based. And after that, we will present you some really low-scale, high-resolution friction studies to understand both surfaces. And after that, we come to more applied energy systems before we come to a short summary. So to give you a brief overview where we are based, so you see here a map of Germany. You see here Berlin and the Dutch and Belgian border. And here at this side, between Cologne and the Dutch border, you see these two big holes. You see here these diggers, which are really impressive. So if you have a chance to come by, that is really impressive to see. And if we zoom into this, here you see these holes. There you see this research center, which is really big, one of the largest one in Europe, with about 7,000 people on campus. And you see from the size, it's as size as Jülich, but then you can also see what the size of these day mining is at the moment, how we get our energy. So therefore, we are really interested in changing our energy landscape. And at the Institute, we are looking at two different pillars. One is the energy storage pillar, one is the energy conversion pillar, where we're looking at advanced lithium-ion batteries, looking at anode-free batteries, all solid-state batteries, but also beyond lithium batteries, sodium-ion and metal-air batteries. In the energy conversion pillar, it's about electrolysis a lot, for CO2 electrolysis. We cannot go through all of that, unfortunately, today. So we will have picked some of these studies we are looking at. And if you're interested in more, please feel free to contact us. What we also always want to do in the end, right? We would like to improve our device. So in this case, if we have a battery, now we would like to have a better battery at the end of our studies, and therefore we are looking into these nanoscale layers inside this battery. But we can also go down to the atomic level where we have the interface, where we have individual atoms. So there's always an issue at which scale are we looking with our techniques, and so we have to basically bridge a different length scales. On the other hand, we have to look in which environment are we looking at that, and you will all agree that is fish, but you also will agree that this fish have different properties than this one is in its natural habitat, and even better in operando studies instead of in situ studies. So we want to go into the direction here of in operando studying energy materials, and for that we have a different approach at the institute. So you see here the length scales from angstroms, electron transfer processes towards like the components, as well as a time scale from femtoseconds to years. And in the end, we have the device degradation and device performance, which we need to improve. And for that, we have to go all the way from down the electrons and the ions, the nanoscale. We do that with theoretical calculations, but we also do that with experimental validation so that we can have here a full circuit from the small scale to the large scale, from really fast reactions down to looking something over years. And how can we do that at the institute is that we are correlating and operando techniques. So we have NMR repair available, but also different microscopy techniques, which are bridging then different length scales. But also we come here with the impedance spectroscopy on the applied processes, which we can also do on smaller scales, and therefore we can have a bridge. And the other really thing, or really part that we think is really important, is looking at in operando techniques. So we're looking at in operando tomography, in operando nuclear magnetic resonance, so spectroscopy, different microscopy techniques. And in-house, we do it, of course, smart. So we have an in operando spectroscopy department. We have the in operando microscopy department. We'll focus on today on these atomic force microscopy, especially electrochemical atomic force microscopy, but we can also do the in operando tomography. And in atomic force microscopy, we basically have a cantilever with a sharp tip, and there we record the deflection of this tip in horizontal as vertical deflection, so we can get information about morphology and topography of a sample, but also about the friction from the torque of the cantilever. And Ini will explain that in a second even better. But you have also the possibility to put that under different conditions. So you can measure electric currents, but you can also put it directly in an electrochemical cell. And since we are also looking in battery research, we have a Bruker system, Bruker Icon system, installed in a glove box so that we can really look at metallic lithium battery materials, anode-free materials directly under these conditions here in the lab. So we are really interested in using these different kind of electrochemical atomic force microscopy for microscale analysis, but also in operando studies. I will show something about that in a second. We're really interested in mechanical properties, which we can show only a bit, except if you say friction is also, of course, a mechanical property. But here we are also interested in hardness and Young's moduli, as well as really locally resolving the electrochemical parts of our surfaces. And with that, I will hand over to Inhi, and she will give you a brief introduction or a clear introduction into like nanoscale friction studies with electrochemical atomic force microscopy. And then I show you something on more applied systems later. Thank you.
Hello everyone, my name is Ini Park. Now I would like to explain about AFM, atomic force microscopy, and how do we use electrochemical atomic force microscopy. So this image shows typical AFM images. So AFM probes scan the surface, and there are interactions between AFM probe and sample, such as attraction and retraction. So due to this interaction, the AFM probe bends toward the sample, or out of the samples. And this bending can be detected by the laser, which is reflected on the backside of the cantilever. Therefore, it's very important to locate the laser well on the probe and adjust the detector. So then how do we measure electrochemical AFM? So for that, we need electrolyte contact with the sample, and the sample is working as a working electrode. And the difference between air measurement and electrolyte measurement is that the cantilever is in the electrolyte, so laser will travel from air to electrolyte, and the reflected laser will go from electrolyte to the air. To apply the potential, we need additionally counter electrode and reference electrode. So if you want to know more in detail, then I will tell you later on. So then what is the friction? We are living with friction every day. So for example, the example is that when you ride a bike, you want to go uphill and you're pedaling more and more, but you feel really hard, especially your thigh you would feel pain in your thigh. Why? Because there is a friction against the moving direction. So in principle, friction occurs whenever two surfaces rub against each other. Then how do we get friction by AFM? So when the AFM probe scans the surface left to right or right to left, there is torsional force which is applied to the AFM probe, and these make the AFM probe twist. And the twisting of the probe contains the friction. And due to the laser location at the detector, the trace scan has negative value of friction and retrace scan has positive value of friction. Therefore, we need trace and retrace scan, both of them. If you are interested in how to evaluate the friction data, I can tell you later on. Then, this equation you might see already and during middle school or high school. So the law of Euler and Hamilton's explain that friction is proportional to the normal load. However, this is not always true, especially for nanotribology measured by AFM. Then why? Because there is an interaction between AFM tip and surface, which can be modified by electrochemical reaction. So for better understanding, I will tell you the other way around. So if there is some change of interaction at the surface, then it can modify the interaction between AFM tip and surface. Therefore, friction will not be all the time proportional to the normal load. Then now I would like to show you an example which I measured during my PhD thesis in Bonn under the supervision of Professor Baltusha. So this sample is iodine modified gold 111, and the electrochemical system is silver containing electrolyte. So the silver will be deposited by a potential sweep or dissolved into the electrolyte again. But interesting part is that silver will be deposited underneath the iodine, so iodine will stay all the time as a topmost layer. Then now we were going to look at friction data. So 0.51 volt, so before silver deposition, you can see at the topography image that there are large terraces and steps. The friction image matches with topography and additionally shows that friction is higher at the step edge. So remark that the darker color indicates higher friction. And when the potential swept, this blue line, so first, second, third, UPD peak, then topography shows nothing, relatively nothing, but friction shows that there is something is going on and it's influencing on friction. Then when the potential was kept at third UPDP, then topography and friction shows some incompleted layer, and then friction shows additional information that the bilayer has lower friction compared to that on monolayer. And then when the potential swept back to initial potential, as we saw in the blue image, topography shows no meaningful changes, but the friction shows that their surface is changing by sweeping the potential. So it indicates that friction change correlates with the change of surface. So we can know by measuring the friction how the surface is changing. Now I'm going more in detail about atomic resolution. So as I said before, I used iodide modified gold 111. So in normal low, there is always iodide layer. When I increase the normal low, then the lattice structure changes smaller. And then for the B potential, there is even more changes. So it indicates that AFM tip can penetrate into iodine layer or even silver layer. Then now I will show you how this penetration affect the friction. This is the friction data as function of normal load. And if you look and the color code is matching at the cyclic photometry, so it shows there is steep increase. For the blue case, there are twice increase, and it's matching with the penetration into iodine layer or silver layer. But for the gold case, there is no steep increase. So probably it means that there is some interaction changes. We have to study more what kind of interaction actually happened there. But it indicates that friction measurement can show the surface reaction, or if something is happening at the surface, then we can immediately see by friction measurement. Therefore, friction measurement is very important. I want to say like that. And now Florian will show you more about friction on not energy material.
Yeah, thank you, Ini. And Ini has shown you how we can measure with friction different states at the interface. And we use this to study perovskites. Perovskites are an interesting material. In this case, we use lanthan strontium cobalt oxide and lanthan strontium iron oxide, LSCO and LSFO, because we can use them for water splitting devices. And water splitting devices become more and more important to get our green hydrogen produced, whereas the hydrogen evolution reaction, HER, is not really the issue because there's only a low overpotential. But if we look at the positive reaction side here, the oxygen evolution reaction, then thermodynamically this would happen at 1.23 volts. But we see that we have a huge overpotential for the current materials we have. So we need a lot of energy, and we would try to minimize these overpotential here for the oxygen evolution reaction to get really good water splitting devices. And for that, we are collaborating with Felix Gunkel here, also from the Forschungszentrum Jülich, and also Karin Kleiner. Now she's based in Canada. She's responsible for the spectroscopy of these surfaces. Felix Gunkel produces these surfaces in a really nice epitaxial way and is doing the electrochemical benchmarking. And we are responsible for the inoperando AFM of these materials. And what you can see in the electrochemical signatures, these are cyclophotometograms recorded in the electrochemical AFM cell. So they are not as perfect as you would expect them to be if you would record them in a proper or in a real electrochemical setup. So they are not as good, but the important features are all there. And what you can see here is the current density versus the potential. So you see already we go to much higher potentials than we would like to go to. And you see also here the number of cycles. So if you cycle from 1 to 30 cycles, they are decaying the current density. So the material is degrading drastically. And if you compare how quickly, then you see that here in this figure D, for the blue material, which is the LSCO material, we have a direct, quick degradation or an early degradation, and it stabilizes at a really low level of the current density, whereas for the LSFO, so with the iron material, we have a rather slow decay and degradation of the material, and the decay stays at a higher current density. So in principle, the material is more active at higher cycle numbers. Here is also an example for the lanthan strontium manganese oxide. which is in between. So our idea was that we can study this mechanism really well with friction studies, because if there are changes in these potential range here, we would see them directly in friction, although they not might appear in the topography images. So to start with that, we looked at the topography of these two materials, and you see before they are run, you see here a stepwise structure. They are really nice. They have some defects from time to time, which then is also seen in the friction. That was also what Ini showed you with the step edges. But in principle, we have a really homogeneous friction distribution on our materials before we use them electrochemically. So that changes then when we use them electrochemically. And here you see something which we call frictogram. So there we plot the friction values in the same diagram as the cyclothermometry. So we plot them on top of each other so that we can relate exactly what happens there. And then you see from over the whole potential range, there's not much change in the friction. So we can say, although we are cycling the material, there's no recovery of the interface. And in this case, the color represents again the friction force. So these are friction force images. And you see from the first to the 30th cycle, there's a huge change in the color. We also see that in the values, where it's here at about 7 nanonewton friction. We are here reaching like something about 50 nanonewton friction after 30 cycles. So the material at the interface is definitely changing, but not within one cycle, but with as a function of the cycle number. And that is the same in principle if you look at the LSFO. There the numbers are a bit different. So here we have just 2 nanonewton of friction, but in principle we see the same effect. So it is shown, or it was shown by spectroscopy, that the degradation mechanism of both materials are a bit different, and we want to understand a bit more. So we zoomed out, and I can just recommend to all of you when you recorded friction force images, so you were in contact with your AFM tip, that you zoom out and see if you produced any damage of the material, but not just to probe, oh, you have an artifact, but also to learn something from that. So in the case of LSCO, we see this square here in the middle where we scanned before, we zoomed out, but there's not much change in the height. We can see the borders, but there's not much change in the height level. And also in the friction channel here on the right, we see that the color is basically not changed within this part. So what that means is that we get a bulk-like degradation throughout our material, and there's no surface film. However, for LSFO, this completely changed. So now we have a surface film that is growing, also shown by spectroscopy methods. So if we see this square, it has a completely different color. We can measure the height. You see here, there's a clear removal of the material, and also in the friction channel, we can now prove that it must be a different material from the bulk setup as well as what comes on top of the surface. So we can really follow these differences in the mechanisms here. Also with friction force microscopy, which is more difficult than with other techniques. As a last aspect, I would like to show in a remaining couple of minutes that we cannot look just at the interfaces and study like, let's say, the chemistry of these interfaces, but we can also follow the dynamics of our materials if it is, in this case, an ionic liquid. Ionic liquids have the specialty that they form these nice layers. So if you have a gold surface or any other metallic surface which is really smooth and you apply a certain voltage, then ionic liquids form a number of layers on top of the surface, and then the tip penetrates through these layers, and then you can see these interfacial layer of the ion liquid in front of the electrode. And here are examples for that. So in this image B, you see basically when the tip is far away and then is approached. So here from 5 nanometer to the interface, then you see these jumps. And these jumps have the distance of one ionic pair layer. So we can now really count how many layers we have here adjacent to the interface. And here you see a double step. So you see first 0.3 nanometer and then another 0.5. And if you look at the friction force image, so it's again not the topography, there you don't see much, but it's a friction force image. There you see here a lattice resolution of the gold film. So in this case, with this stick slip pattern, we can analyze the dimension, and we can clearly say that is a gold film, and that means our tip penetrates through all ionic liquid layers. So the 0.5 would correspond to the anion while the 0.3 would correspond to the cation layer, and then we get the high resolution. However, typically we do not see an atomic or lattice resolution in these cases, but we see something like this. So in this case, there's no crystalline structure to be seen, but we see if we change the potential, in this case, positive potential towards negative potential, that the friction changes. And if we look at the force distance curve, so penetration of the tip through these layers, we see that the layers also change. So the larger distances remain the dimension of the ion pair, whereas the interface distances change to cation and anion layer. And now you might wonder, if we have a positive potential, why this is the cation. That is just because we're scanning here not at the substrate, but we're scanning at these anion layer. So the first layer which you penetrate through is the cation, and at negative potentials, vice versa. So we can see here that we are not at the gold film. So if we now look at these layers and put them on top of each other, I will overcome these images. Or what you can see here is basically, if we record a cyclothermogram again in these ionic liquid, that we basically have at each of these signs where we see something in the electrochemical signal also have changes in the friction. So showing again that friction is really sensitive to our changes at the surface. So if you look at these interface again on the gold surface, minus 2 volt, minus 1.5, and minus 0.5, then we see that indeed the substrate, in this case the gold, you see here the steps, is not changed. You can see the step structure in all of these images. The color is again representing the friction. So the friction is clearly changing as a function of potential in these ionic liquid, while the substrate remain unchanged. And we see that these ionic liquid layers change drastically at negative potentials. They have a way more ordered structure than it's only slightly negative potentials. And now we were interested, if we now switch the potential, then it was published quite some time ago that there are different reorganization processes taking place at in the order of milliseconds. The cation and anion transport, this is really fast. Also, the reorientation is in the order of 100 milliseconds. But which is really hard to measure is the lateral 2D reorganization in the order of many seconds. So we thought lateral 2D reorganization, that is something exactly what we can probe with our friction force microscopy by electrochemical AFM. And the result you see here. So that is again switching from minus 1.5 volts to positive potentials, recording the potential. You see that here, changing the potential from minus 1.5 to plus 0.7, as indicated here as well. And then parallel recorded the friction force. And you see when we change the potential, then we have here a change in the friction, which then decays again and then stabilizes over a long time. At the same time, we can look at the current. So this is the capacitive current we measure here, and we can do that for the other direction as well, switching from positive to negative potentials. And then we look at the friction again. And here we see, after this initial decrease in stabilization, we have here an exponential decay. So from this, we can now calculate all these different numbers, and then we can get information how long do we need to have at this interface a real stabilization, which is, of course, if you use ion liquids and energy materials, really important that you get a stable interface again. And then you see that these relaxation times change drastically. So for the current, the capacitive current is rather fast when we switch from positive to negative, but also really slow or getting much slower if we switch to the other direction. And friction behaves also drastically different here. So we have a strong dependency on the direction of the potential step. And the first relaxation times, so if I go back the first times until the friction stabilizes here, they are rather equal for both directions. So from that, we can learn something about our really switching behavior if we have energy materials in that. With that, we come to a summary and acknowledgement. So we have shown you electrochemical atomic force microscopy. Importantly, the tip is an observer and not really actively part of the electrochemical setup. So this is different to scanning electrochemical microscopy. Ini Park has shown you the really high resolution atomic stick slip patterns and showed you that we can differentiate between different adsorbates and functional layers on really high resolution. Which is then also helpful in ionic liquids to determine on which layer you are really measuring, and can follow the the changes in electrochemistry, and that is also something we can look at the dynamics. And that is just the short overview of what we do in friction analysis in our lab for our energy materials, for example, batteries. We are also interested in mechanical properties, which we probe differently, which you might have seen on the poster in the back. But if you have questions to this, please ask later. We're happy to help. So big thanks to the entire group who is involved in these studies. Of course, the funding agencies, which is mostly the DFG and the BMFTR in Germany. And of course, thank you for your kind attention, and we're really open to questions. Thank you.
Thank you both very much. Fantastic talk. So we've got 2 questions at current. I'll go through the first of those now. Just for anyone else, please type questions in the chat, and we can address those. We have a little time before we'll need to move on to our next speaker. First question is from Julian, who asks, "What are the timescales of AFM images and electrochemical measurements in the friction versus E data?"
Yeah, so of course that is highly important. It depends exactly of what you want to do. So it can be rather slow. So typically we record the AFM images for the one cyclovoltammogram. So you adjust it at the time of the AFM image, match the time of the cyclovoltammogram, which is then typically that you can really measure something and see it on these typical timescales of the AFM in the order of minutes. So we record between 5 and 10 minutes for one AFM image. But you can do it, of course, much quicker if you are not recording the potential at the same time, or if you're switching the potentials, then you can go down to really a couple of minutes. But if you, for example, just measure the Z component, so the force distance curve, there you measure in the range of seconds. So the typical AFM, as I would understand the question, is in the order of about 10 minutes, something like that.
Okay, that's great. Thank you. Our next question is from Xiaoli, who says, "Hi, thank you for your presentation. I have one question. During the friction mapping acquisition, you must use a cantilever with sharp tip, really low force constant. And did you check the geometry after tests? Do you have any recommended methods of measuring the tip if it is worn out?"
Yes, that is, of course, really important. Thanks for the question, to pointing out that is indeed important. So we use really cantilevers with a low force constant so that we can measure the friction well. So by zooming out, for example, you see if there is any problematic with the tip. You also see it depending on the resolution of your images. If you go to the really high resolution, that the tip is not really affecting something. So that's something we prove while we're measuring. But we have seen, for example, in the case of metallic lithium, where we measured the mechanical properties of metallic lithium, the tip is really worn off. That comes from lithiation of the silicon tip, although we tried everything to avoid that, for example, by using a potential where the tip should not be lithiated, but it still happens. And then you typically see on your images patches which have the same shape and geometry. And if you have a couple of times the same features on the surface, then you should take care. That is usually a tip effect. So you can see something of that. And then how we measured really that the tip is not worn out. If we have sign for that, you have to go to a scanning electron microscope with a certain holder where you put the cantilever in. You need to put them in for a long time before they are stabilized. They always vibrate a bit. But there you can still see if there's a significant worn of the tip. But otherwise, when measuring, you get some hints during your experiment as well.
Thank you very much.
But important questions. Thanks for pointing that out. Yeah.
Absolutely. I was curious as well, in addition to probe geometry, is there any difference in the probe materials used compared to sort of what we may say more sort of traditional AFM, where it is mostly just topography? Are there any different materials that would be favored for the tip? Obviously, the force constant is low, but the actual probe itself?
So typically for the
Mhm.
electrochemical friction force measurements, that is a typical silicon tip.
Got it.
What we usually are not using is a coating on the backside, because if that is damaged, the liquid might penetrate that, and then
Yep.
the calibration is off. So we typically use silicon, so doped silicon, to not have any charges at the tip. So silicon nitride also has some issues without any certain coating. But for the example, when I used the which I brought up on the metallic lithium, there we swapped then to use diamond tips, because they have not this issue, and then you can compare the typical conventional tip with the diamond tip, and you see a completely different behavior. So you know that also that comes from the tip. But for electrochemical friction force microscopy, what we demonstrated today, that is a normal silicon, doped silicon tip, without conductive or without a layer for the without a reflective layer. That's the
Okay.
And within silicon tip, there is hard cantilever and soft cantilever. So for a hard cantilever, you can usually apply from 0 to 100 over 100 nanonewton, because it's more resist to worn out or something else. But soft cantilever is detecting more sensitive to the from the surface. So even though we apply low normal load like 1 to 2 nanonewton, but we can immediately see some atomic resolution or what's happening on the surface more sensitively. So you can choose depending on some electrochemical and how sensitive is the surface. So yeah.
Okay, thank you very much. We have another question here from Jiaoyang. I hope, I'm sorry for the pronunciation, but however, they say, thank you for the nice talk. Could you please introduce how strong tips wear? I guess talk about the mechanisms of that. And if yes, is there any idea how to reduce such tip wear?
So typically, the answer is that not the tip is wearing off, but that the surface is getting damaged, and that you can, of course, avoid by using a really low normal load. Of course, we're doing it in electrochemistry. That means we have not much of adhesion force, so you need to have a bit of a normal load, but reduce that as much as possible that you get a stable imaging. Then the wearing off of the substrate of your sample is getting reduced, and typically that is the more problematic part than that the tip gets worn off, except for the example for the metallic lithium. But here in these cases, it's typically not that there's a strong tip wear.
And for my experiment, there was no wear effect. So it was irreversible. There was no irreversible wear. So which means that if I sweep back to the cathodic sweep and then after anodic sweep, there is a totally same from compared to initial stage. So it's always depends on the sample and electrochemical system. So you have to check all the time if there is a wear or not.
Exactly. So this is really important questions. So that's why I also said zoom out and see if you see the damage of the surface, or do you observe any patterns that is of a similar symmetry or shape, and then you get a hint of that. But it's really important to look for that, because yeah, you're absolutely sure what we measure is in principle depending on the surface area, and that if that changes, then we can't rely on the numbers we get. So yes, important to check.
Okay, brilliant. Thank you both very much. Looks like that's it for our questions. So I just want to say thank you both for your excellent talk and for your great explanations regarding, I think everyone's very curious about AFM tips today. So that's good to see. So I think
Thank you very much. Also for the invitation to show something.
Oh, you're very welcome. You're very welcome. So now I'd like to just sort of say thank you very much to Brooker for the partnership for this event, and Dr. Khaled Kaha will be our final speaker for today. I've already released a couple of the handouts, which I've been indicating in the chat, and all the poll questions are there. So if you have not answered those, please do look at that. Please do look at them. We've got one final handout, which I'll release during Khaled's talk. But without further ado, welcome. Thank you very much for joining us, and
Thank you.
I'll stay on stage a moment
Yes.
just to check whilst your screen share is set up.
Thank you. Let me share my screen. Voilà.
Okay, fantastic. Again, that's as I said when we were looking at the slides before, that looks delicious. But anyways, stage is over to you.
Yes.
Thank you very much. And
Thank you.
there we go.
Okay, perfect. Well, thank you very much. Thank you for organizing this. And thanks for everybody for assisting in this and for the former speakers too. So I actually intentionally started with this image, well, because it looks delicious, but that's exactly the point. Well, basically the idea here is if you go to any fancy foreign restaurant and you see a fancy name of a dessert and you order it, then you see it and it looks pretty nice, but you don't really know what it is. Then you taste it. Then when you taste it, you might speculate a little bit about what it's made of. So you know its functionality. But you cannot know what it's actually made of. And this is exactly the problem that I would like today to solve, but not obviously with dessert, but with surfaces at the atomic scale. So I'm currently working with Bruker as an application scientist, and I'm based in Karlsruhe in the Bruker Nano Surfaces and Metrology division. So my talk today is going to help us understand how we can go now from seeing to knowing what we are looking at and what causes or affect the functionalities that we measure with these different modes that the former presenters showed, basically like electrical, mechanical, electrochemical. So these are functionalities of the systems that we can understand with different modes in AFM. But now we would like to push the boundaries and unravel the actual chemistry of these surfaces, which will provide us with much further insight to understand what is causing these functionalities to happen or to change. So the goal of my talk is going to, first of all, tell you what is AFM IR, so AFM coupled with infrared, how it works, there should be an S, and I would like to also tell you how this gives us much deeper insights at the nanoscale, so we can understand or study local spectroscopy measurements and chemical ID mapping. So as you will see in this presentation, then this will help us improve the understanding of the surface properties with the complementarity with the other AFM modes. Then I will go through a very quick overview of different applications, including the applications into energy materials, but not restricted into that. And I will give you some examples from the latest literature on the results and developments in this technology, and I will end up with my conclusions. I would like to thank also all the participants who answered the questionnaires, and I see that many people have heard about AFM-IR and some have not. So hopefully today this will help those who haven't heard about it to learn about it, and those who have heard about it, if there's any unclear things to be clarified today. So to start, I'll be talking about the photothermal AFM-IR. But let us go to the very basics. So perhaps most of us have seen in, whether it was in chemistry or in physics studies, you must have learned or maybe used afterwards these conventional Fourier transform infrared spectroscopy. So this is a very common technique used in different fields to basically understand the chemistry of substances, right? So we send the light, an infrared light, into a substance, which could be made of a liquid or of films or whatever, which contains molecules that have energies to rotate or vibrate. And then if the energy of the light coming into, so let me just maybe put this one. So if the energy of the light coming into these molecules matches their energies, then they will absorb it and they will actually move. Then what we measure in conventional Fourier transform infrared is the amount of transmitted light. So whatever is absorbed, we know basically which molecules have absorbed it. So if we all agree on this Beer-Lambert law-based physical principle, because we know it, then this is not how it works in AFM-IR. The reason why I am saying this is because many people tend to think, well, doing IR, AFM, we should be doing something like this. We are not doing something like this. So let me explain to you how we do. Obviously, the physics is the same in the sense that infrared light will be absorbed by materials. But how do we measure it with AFM? So from a steps sort of perspective of how the flow of measurement happens, basically we will be sending light, infrared light, focused into the surface. Then this light, if absorbed, will cause the surface to deform, to expand due to local heating, which we call the photothermal absorption. And this deformation of the sample, we actually know very well how to measure it with AFM. And this will allow us, from the magnitude of this absorption, to reproduce spectra. And I would like to use this animation here because it actually helps me a lot visualize how things are happening. So this is a cantilever touching the surface, and this laser here is the one, it's optical lever to measure its deflection. So when we send an infrared laser to the sample, the way we imagine it like this, if the wave number of that laser can be absorbed by the sample, it will be, and the sample will expand, pushing the tip upwards. So when the tip is pushed upwards, the cantilever will bend. And this is exactly what we measure in AFM. Now, the amount of this pushing, the amount of this expansion will give us different bending. However, if I just do a quick stop here, however, this expansion is pretty small. It could be a few picometers. So we need to enhance the signal that we can measure with this. And here, to do that, we use the so-called contact resonance approaches, which means that instead of sending the laser, infrared laser, to the surface statically, we send it as a pulse. So basically what you see here is the laser is pulsed into the surface. So it's on, off, on, off. So every time it's on, the sample will expand. And when it's off, it will retract, expand, and retract. And this will happen at the same frequency of the pulse. Now, if you watch it here, the sample going up and down is basically activating now the cantilever because it's pushing it up. So if the frequency of this pushing up and down, which is basically the frequency of the laser pulse, if it matches a contact resonance eigenmode of the cantilever, then the cantilever will get into very high amplitudes of vibrations in contact, which enhances the sensitivity of our measurement. So we will be measuring this, and if the amplitude of this expansion changes due to the absorbent properties, the amplitude of the cantilever vibrations will change, and that's how we reproduce basically the spectra due to the change of how much the sample has expanded, so how much it has absorbed the infrared light. So hopefully this clarifies for those who haven't seen it before or maybe was not clear for them how actually we measure it. So basically we measure with the probe the change of the surface due to the infrared absorption. Now, this allows us to do two things. The first part is spectroscopy, right? So similar to what you would do with any infrared study, you would want to see the absorption spectra on the surface of your sample. In that case, we will position the tip on different areas of the sample. So obviously we are using AFM, so we can image the surface. We can do that either in contact mode or tapping mode or force curve based modes. I'm not going into these details now, but basically you get an image of the surface, even in peak force. And then you position the probe, you choose positions of interest on that surface. And at each position, the laser pulse, the wave number of the infrared laser will be swept. And the amplitude of absorption will be collected, creating these local spectra. Now, what's interesting is, see, for example, this 3D representation here, the scan size here is 100 by 100 nanometers. So now when we speak about spectroscopy, right, we're speaking about nano-localized spectroscopy, which basically allows you, if you already do normal infrared spectroscopy, to gain hugely in terms of spatial resolution and discriminate between local changes on your materials, something that you will see it weighted, or let's say averaged with a normal infrared. Now that's one thing. The other thing is where when we come to see things and add into it the understanding of what we are seeing. So this example is a topography image of a copolymer nanostructure. So you can estimate the size by looking into the scale bar, right? So this is the topography. Now, instead of doing spectroscopy now, by sweeping the wave number of the laser at one fixed point, we will send the laser pulse at one specific wave number all the time, and then we will scan the surface. So what happens is, we will only measure a bending or amplitude of the cantilever only at areas of that surface where that wave number is absorbed. So basically, well, I have turned my Teams off, but still popping out messages. Anyway, sorry for that. So we will be imaging only where the absorption happens of that wave number. So we will have a map of absorption. Like, for example, on that structure, if we have sent basically the wave number of the laser pulse at 1492 centimeter minus 1, which is the one corresponding for an absorption for polystyrene. And then we start mapping, imaging in topography, parallel to the topography at the same time. It's based on lock-in techniques. And then we basically see that those areas of the sample are the ones that have high absorption, while the rest is not absorbing. So we would know then that these areas basically must contain polystyrene. Now you can switch the wave number on the same sample, same area. You do just a second scan by switching the wave number of the laser. Then in that case, it's the one corresponding to PMMA 1730 centimeter minus 1. And then suddenly you see that the contrast of absorption totally changes, because only now the areas with PMMA are the ones that are absorbing. And these arrows here are meant to show you the resolution of these changes in the chemistry mapping. We are around or even better than 10 nanometer. What is nice is we can overlay these two contrasts on top of the topography, and now we know the nature, the chemical nature of what we are seeing. And as I will show you, you add to that the other properties of interest, functional properties, then it's about actually to have a great understanding of what's going on your system, especially if it's a newly developed one or has any changes that happen with time or external stimuli. And this is exactly what I want to show. So these results here are made on a typical, we call it like a reference sort of sample, because it allows us to put forward these features of the measurement and the modes. So this is a blend of polystyrene and LDPE. So the polystyrene is the matrix, and LDPE are these bubbles, basically. So we know what the sample is made of in that particular case. Now, the thing is, with the methods available, and again, I thank you for answering the questions in the questionnaires about that. We can measure, for example, the surface potential using peak force KPFM. And if we do it in the frequency modulation, so that's basically the peak force KPFM mode, if you have it or if you are interested in it, we are able to measure in parallel the capacitance gradient variations. And this is something that I published 2 years ago. You can find it. It shows you how we can measure the capacitances variations. Now, at the same time, on the same sample, since we are basically using peak force combined with Kelvin probe force microscopy, which is the surface potential measurement, so the peak force allows us basically, because it's based on the quantitative nanomechanical mapping, to get at the same time the mechanical properties variations, like the adhesion. So the adhesion here is the as Tobias showed it. So that's the adhesion of the tip apex, or between the tip apex and the top surface of the sample. And the Young's modulus, which is the modulus of elasticity. So obviously here, clearer is higher and darker is lower for all these color scales. Now, these things you can get on the system, on any system, I mean, on any system, on a Bruker system that, let's say, is equipped with these peak force QNM and peak force KPFM modes. Now, if you use the system that has, in addition to that, the capabilities of doing the IR, for example, the ICON IR system, then similarly to before, you can map in that case, after you do local spectroscopy, the chemical ID. So when we do local spectroscopy at these different points, obviously at the point, the red one, where we have the LDPE, we see actually peaks that correspond to the absorption of LDPE. And then on the polystyrene, we see peaks that correspond to polystyrene. So we can make our choices such that we don't see, so we can discriminate between the two materials. So 1493 will show us basically that the polystyrene is the one that's absorbing. So higher contrast here is the green. And when we switch again the wave number of the laser pulse, then we are actually looking to the absorption of LDPE. Regardless of the importance or not of that sample, the goal of this slide is to show you that with same tip, same area, same conditions, same samples, you can get all of these information. And obviously, this is not the highest resolution. You have already seen in the previous slide how much resolution we can get, and you will see even more better resolution in further slides. So that's the goal, is to give you this feeling of what one would be able to get with this technology. So speaking of what we can get, maybe I can show you a quick overview of different applications, including energy materials. So with the help of my colleague and much more expert in AFM-IR than me, because I come more from an electrical AFM background and I'm now getting into the AFM-IR. So that's done by my colleague Hartmut Stadler in Karlsruhe also. So you can see here, it's just an overview that this applies obviously in polymer sciences. So because when you do polymers, you are intrinsically interested in the chemistry, right? So blends, films, composites, all these type of measurements. But this also all expands to life sciences. So looking into cells, for example, or life science-based films or applications, this also is of interest. We can see that also in environmental science. So like, for example, looking into nanoplastics or microplastics or even geosciences. So the main people basically that we collaborate with very closely and who are at the origin of the main idea of this one. So Professor Alexander Dazi in Paris, Well, they look actually into meteoroids samples, right? So you can actually make, and even paintings. So these are very interesting applications too. Pharmaceutical science also. So if you look into drugs, and I will have some examples afterwards. Now, materials, obviously. So like batteries, battery materials, catalysts, 2D materials. So basically any type of material where you can have a signature in the infrared range of interest that you can see. And in semiconductors, which basically is mostly important or interesting for looking into different contaminations and thin films and processes of cleaning or these sort of applications. So I will show an example here. This is not a published example. This is one done in our labs for testing and for the purpose of showing results about it. Is a cathode material. So it's a lithium battery cathode where we can see the topography, and this is relatively rough structure. And then if we look into the different properties, so we can see in this direction here, we can see the mechanical properties like the Young's modulus, seeing that some areas which look like pillars actually are much stiffer than other grains. And then we can look also into the current in peak force tuna or in tuna measurements, like the ones that we have seen in the presentations before. We can see where areas are more conductive than others. And then we actually add into that the chemistry. So here we can see that we can identify the presence of some polymeric materials in there. So I have done some other measurements. Well, I haven't put them here actually. When you use how to say this, when you fabricate new materials for cathodes or anodes, and you have different chemistry, you have some binders and then you have some active materials. This sort of measurements allows you to identify which chemistry is where and which chemistry is the one helping in the conduction or not. Another example is more for the nano contamination. So the image that you see here is an overlay of multiple infrared absorption maps. Each one of them is obtained at different wave numbers. So that's where the color indications here. And the goal of that is to show you that any contamination that you see on the surface is basically made probably of different chemical contaminations that you might be interested to understand depending on your application. And the spectra that you see in here are for different positions, as you can identify in here. And then we can see the presence of the substrate. There's some particles, silicon oxide, the carbonyls, and different chemical. I'm not a chemist in basically, so I leave that mostly for the chemists because this speaks like that for them. I'm more in the physics side of that, but getting into the chemistry. I like this example because this is done out of a test, and I've told you that I will show this earlier. So basically, my colleague, Dr. Stadler, just went out to the pharmacy and get an inhaler drug, and then actually prepared the sample with these particles inside this inhaler drug and looked at them in AFM IR. So you see these particles in here, and you can actually identify with different contrasts obtained at different wave numbers. So each color here is obtained from a map, AFM map, where the laser was sent, or the laser pulse was sent at one given wave number. So the green area is the lactose, the blue area is the salmeterol. So you can identify basically image-wise the different components of the drug. And obviously you can go and take different positions and extract the local spectra there. So this is very interesting for industries or research on drug delivery, because we, as you will see further in the slides, we also have the possibility to image not only on the surface, but even go below the surface. So be sensitive to information from below the surface. And that's where you can think about chemistries in a shell, where basically we will be able to look at them. Now I will move on to some examples published in the literature, not just application examples. These are not examples related to energy materials. So I took the liberty at the end of this event to actually spread a little bit away from the only specific applications and thematic of energy, because this will allow us to project this technology into much more wide sort of fields. So as I mentioned, the main inventor, if you want, of the idea of using atomic force microscopy to measure the photothermally expanded surface of a sample is Alexander Dazzi. And we collaborate very, very closely, and we work with him on this technology. So Professor Dazzi published, I think it's 2025, so it's earlier this year, this very nice result. And I was in the lab when this was popping out on the screen. So what you see in here is a surface of self-assembled monolayers. And it's extremely thin surface, so that's like a single monolayer. So we are speaking about a film around 1 nanometer thick, so a very small amount of matter, of volume of matter. But we can still we are still sensitive enough to this film, and we can measure the change of their infrared absorption properties. And you can see that when we look into the same area at different wave numbers, that we have the change in absorption when we have a specific wave number and not on another one, indicating that this is basically chemical ID related contrast. Now, what's interesting is that this contrast, if we take a profile, we have a change in the variation of these self-assembled monolayers. So these are molecules that are aligned, basically. We can see the discrimination, if you want, laterally speaking, with a resolution around 2 nanometers. So I don't know how much this would speak to many of you, but let's put the message like this. We are discriminating areas on a surface with different chemistries with a resolution of 2 nanometer. And this is starting, right? So obviously this can only go better. And it's about imagining where you can go with that and what you can do with it. The second example, which is also, I mean, it was deposited as an archive, but I think now it's published. So this is a collaboration between Brooker and UCSB in the States. It's about 2D materials in that case. And well, 2D materials here, we are looking into a result that's related more to the structure of the 2D materials, but obviously 2D materials like graphene or other like MOS2 and other materials are very present in applications in hydrogen generation and water splitting devices. So what this AFM IR measurement allows in this case is what you are looking at are maps of infrared absorption on different graphene layers. And here we see the contrast at different wave numbers depending on the stacking folds of the different graphene layers. So depending on the type of the stacking, you see a change in the infrared absorption ID, right? And this correlates pretty well with electrical measurements. So these measurements are done in microwave impedance microscopy. So they reflect changes in impedance, in the real and imaginary part, which basically reflect changes in capacitance and conductivity or resistance. And finally, I will end up with this result, which I personally find extremely interesting. because I've been working on something similar, but more on the electrostatic side, electric properties. So this is a first result on the pathway towards tomographic imaging of nanochemical mapping, right? So the result here is also published by Alexander Dazi group in collaboration with Brucker. And here you see an image where you have a 3D reconstruction of a sample where the reconstruction that you see is chemical mapping. So you get images at different depths of the chemical contrast. And then you can reconstruct a 3D tomographic image of that. Now, you might wonder, and I will just put that as simplified as possible, but we'll be happy to answer your questions about it. How could we basically do that? The idea here is based on the thermal diffusion length, if you want. So if you remember that light that have been pulsed into the surface, so every time the light is on, the sample absorbs it and expands. But when it's expanding, there is a thermal heat wave that should travel through that material. Now, if the time, so if the frequency of this pulse is high, the time between the expansion and retraction of the sample is very short. So depending on the thermal conductivity of that material, of that surface, this thermal or heat wave might not have enough time to travel further in the volume of the material. So in that case, we will be collecting a chemical response mostly sensitive to the very top surface. And vice versa, if we give the wave or the heat wave enough time between the on and off of the laser pulse, if we give it enough time to travel through the volume, so we will have a response more depth sensitive. So how does that translate? If you remember in this animation, the laser was pulsed to match an eigenmode frequency of the cantilever in contact because we wanted to enhance our measurement. So it means that if we tweak or adjust the frequency of the laser pulse at the high eigenmodes of this cantilever, then the laser pulse will be sent at very high frequency that could go to up to few megahertz. So in that case, the heat wave does not have enough time to travel, so we have very sensitive, top surface sensitive signal or measurement. And if we adjust the laser pulse into lower values, then in that case, we are more depth sensitive, right? And this is how basically we can get into this. Obviously, if you wonder, and a lot of people ask me how much depth it is, etc. This is a work, as you see, it's a pathway to chemical tomography. So this is a work in progress. And Alexander Dazi and his group are working very nicely on that. So with this final result, I would like to finish with a quick summary. So what I wanted to show you is how this photothermal AFM IR works. It offers a high resolution capability to look into chemical identification and local spectroscopy. So it's now very well established technique, although some people have not seen it yet. So that's one of the reasons why this webinar is expected to help spread more this knowledge. And I mean, this technology allows us to look at very thin materials and have also a more in-depth information sensitivity. And it offers an extremely interesting complementarity to other AFM measurement methods to enable a much deeper insight and understanding of our system. And obviously, it covers many applications that we have seen. And the beauty of AFM in general is that it's really researchers' imagination dependent. So you can imagine it to apply it on many different things. And with that, I would like to thank you for your time, and we'll be happy to answer all your questions.
Thank you very much, Khaled. Just before we get into any questions, well, one, to encourage anyone for any questions, please do type those in the chat. We've got a few minutes in which we can review anything that anyone wishes to ask about, whether that be application specific here or Brooker AFM platform specific questions as well. We can take a look at both. I'm also going to do the link through which you can all download the attendance certificates, but please don't leave the event. That link will remain active for the rest of the day. So open that tab and come right back here whilst we continue our discussions. So we have a question from Tobias, who has asked, what is the scale of the AFM on slide 13?
It's a very good question.
Mm.
I don't have it, but I guess the scale, the scan size should be, I think, around 20 by 20 micro.
Mm-hmm.
Yeah.
Okay. Thank you very much. Whilst we're waiting for some audience questions, since you talk quite a bit about sort of multimetric, or sort of multimode AFM analysis, there's quite a few. Obviously this is focused on energy materials, but we kind of diverged a little bit at the end to talk about quite a few different things. I was wondering what has been, and in your experience as an application scientist, what's been your favorite sample or favorite type of sample to take a look at with some of these multimode techniques? I thought that you've probably seen some I'm sure quite specific things, and perhaps
my personal favorite type of materials to look at these different techniques are 2D materials, like graphene boron nitride stacks, for example, molybdenum disulfide. Although with molybdenum disulfide it's a bit difficult depending on the range of the IR that we have, but basically the 2D materials is the sort of applications and samples that I like to look at different techniques, because first of all, these materials are interesting for many applications, whether it's in energy or material science, even on the mechanics side of things.
Yes.
And this complementarity of methods allows to make a better understanding.
All right, thank you. Yeah, as you were going through your presentation, you were talking, it's like, as someone who is a kind of a physicist at heart as well, and has also sort of branched out into a few other areas, there's sort of some, it's like we gain some skills in chemistry, but there's still quite a bit that sort of hold our hands up and go, yes, we need to learn that a little better. We have a question here from Jiao Wang. I'm really sorry if I'm pronouncing your name very poorly, but they've asked, how is the measured IR spectroscopic data related to materials? Are reference materials needed, or a data bank? Is this sufficient? Or is a data bank sufficient? Excuse me.
Okay. Well, basically, there is a sort of tabulated data for IR signature of different molecules and different bonds and energies. So basically, when you get the spectra from our measurements, for example, then there are some databases like Know It All from Willy, the publisher, that in fact you can upload the spectrum that you obtained, and their software, this database, will allow you to have many suggestions of the known materials, or known energies corresponding, or known molecules, chemistries corresponding to these absorption energies. And I believe this also is an option that you can get on systems from Brooker, basically.
Okay, thank you very much. We have the question here from Nate Buddha, again, my apologies for pronunciation, but they've asked, how do you calibrate the tip and the laser in AFM IR?
Well, I mean, it depends what is meant exactly by calibrate. So, well, calibrating the tip for, let's say, its spring constant is something that we do as in any mechanical property measurement. So you can have different ways of doing this. Either you use so-called thermal tuning, or we use pre-calibrated probes also offered by Bruker, or you use a hard surface like sapphire to get the cross curve. But I assume that the question here is mostly towards how you focus the laser on the tip. So how you make sure that the tip or the laser is well focused under the tip. I would probably think that this is the question in that direction. And for that, I would say that there is a very streamlined procedure where you can use a visible light that guides you, first of all, to position the infrared light, which is not visible. And once it is there, you basically have a procedure that allows you in real time to change the optics and to find your best focus spots and make sure that the laser is well aligned. And once it is done, basically, you don't need to do it anymore unless you change the probe.
Okay. Great, thank you. As well, considering all of these sort of the IR modules and other things, are these modules available on all of Bruker's various AFM platforms? I know kind of the main one is the Dimension Icon, or the Icon Pro that you've got in your background image. Is
yes.
Sorry.
No. So basically the IFM IR, I mean, the IR is not an extra module that you get, for example, on another system like the Icon. So we have two sort of two class of products. So we have the Icon IR, which is basically, and I didn't show that in the slides, but basically it's a device. It's a separate product, let's say. It's an Icon platform. So it's like an Icon system operating with the Nanoscope 6 controller. But then you have also all the optics and the lasers on the same device, basically, operating together. And then you have the Icon IR system. So that's for the first class of products. And the other one is the Nano IR 3, which is basically a system similar to the Icon, but does not have the same AFM modes as the Icon system. It's mostly focused on the spectroscopic functionalities of this measurement. Yeah.
Okay, that's great. Thank you. Whilst we're talking about the various different AFM modes and everything, for anyone that hasn't, I just want to draw attention to the handouts that are available in the handouts tab. So those are on the various AFM modes. There's a handbook for that. There's the comprehensive guide to photothermal AFM, IR spectroscopy, and an ebook on advances in AFM nano electrical modes. So if you haven't had a look at those, please do go ahead and download them. But I think they're also available on the Bruker website, not just exclusive to this event. So,
yes.
Yes. Any further questions from anyone in the chat? Just want to give everyone a good chance to ask anything else. Okay. Seems not. I don't think we have any further questions, Khaled. So I think now is a good time to draw the event to a close. So I just want to thank you very much for your fantastic presentation and running through all the questions. And thank you to our other speakers today, Florian and Inhi and Tobias. Great presentations. As someone who's more of a nano indentation guy than an AFM guy, I've certainly learned a lot today. And let's bring up our end slides as well. Thank you very much to our partner today, Brooker. Without our working with them, we wouldn't be able to run, and our other partners wouldn't be able to run events like these. So it's fantastic to have their support. As a reminder, please do visit the Surface Ventures website. We have our archive of previous recordings. There will be information about our upcoming events in the new year. We're aiming for the 29th of January for our next event, but we will be sharing details about that in the new year. For other updates, please do, you can subscribe to our mailing list, and also check out our LinkedIn page and Twitter/X, formerly Twitter page, for updates. Thank you all very much in the audience for being here today. And finally, I'd just like to say, we hope that you enjoyed the event, and please do take the time to promote this to your colleagues and friends, anyone that might be interested. We're always wanting to grow our audience and tell more people about the the fantastic things in the worlds of tribology, surface engineering, and material science. So from us at Surface Ventures, it's our last event of 2025. Looking forward to more events in 2026, and we hope you all have a fantastic holiday break. Okay, goodbye, everyone.